All right, let's look at another practice question. There is a square with sides L. Two long straight wires are perpendicular to the page and are located at two opposite corners of the square. Both currents are equal in magnitude but opposite in direction. Find the magnitude and direction of the magnetic field at the indicated point. Okay, so this current here and this current here are both the same, but they're moving in opposite directions. So this one down here in the bottom left corner is pointing out towards us, and this one in this top left corner is pointing down and away from us. And then of course the side lengths of the square is the same, and we want to know what the field strength and direction is here. Okay, so the first and easiest thing to do would be to use our curved finger right hand rule so that we can figure out what's the direction of the magnetic field caused by this current, and what's the direction of the magnetic field caused by this current. I haven't put subscripts here like I1 and I2 because it said that they are equal in magnitude, and I didn't want putting subscripts in there to make you think that they were different values in any way. But because they have opposite directions, they are different. So let's do this one here first, okay? So we're gonna use our right hand. We've got our thumb pointing up. On this side of the current, the magnetic field lines would be pointing down, okay? But this point over here is not on this side of the current. It's over on this side. So that means we have to continue curving around so that our field lines are going to be pointing up once it gets to this side over here, okay? So our magnetic field lines on that side are going to be pointing up. All right, now let's do this one, okay? So in this case, the vector, the current vector is pointing into the page, so we're going to point our thumb down, and we're going to curve our fingers then, okay? So this point right here is on this side of the wire. So that means that we have to curve it all the way around until we get to this position. So that means that my field lines are going to be pointing to the left. Okay? So we have something that looks like this. Okay, so now this is B, and we want to know what the magnitude and direction is. Well, we're going to have to add these vectors in order to do that. So that means that we can, remember, you can move a vector. So I'm going to move that vector up here to the top, and the resultant vector is going to be the net magnetic field. So we want to figure out what this is. Okay, we need to figure out what that is. So that looks like some Pythagorean theorem stuff to me. All right, so in this problem, you'll see that I did go ahead and label 1s and 2s so that you could keep track of it. So we have here our vector that we moved up to the top. Then there's that came from this one. Then we have our magnetic field strength vector here that's a vertical, that's coming from this current over here, and we want this net component here, this where we add them together. So we've got a squared plus b squared equals c squared, and take the square root to get just that net magnetic field strength. This is our new equation for magnetic field because of a long straight wire. So those are the exact same thing because it said that the currents were equal to each other. So it's just 2 times that stuff. So then we can pull the 2 out and take the square root of that. This is just squared. So if we take the square root of that, then it just becomes itself. And then the angle here that we have, this vector that's pointing up, I've just drawn a line to match that, but we do need to, kind of figure out what that angle is. And the way that we can do that is by putting a coordinate system on that point B. So if we extend this line out here, and this is 0 degrees over here, and this is 180 degrees over here, this angle, since these two strengths are exactly the same, that means it's splitting this angle down here. So it's splitting that 90, which means that this angle right here is 45 degrees. So you can just say 180 back up by 40 degrees, and that's how we got our 135 degrees here. All right, let's do one more practice question. Two parallel electric currents a distance d apart are in the plane of the page. They both have a length of L, and L is much bigger than d. This means they can be considered to be long straight currents. Find A, the electric force, and B, the magnetic force acting on I2 by I1. Okay, because L is much, much bigger than D, we can say these are long straight currents. This is the same idea as when we were talking about parallel plates, and we said that between parallel plates we could have electric field lines being set up, a uniform electric field line, but that at the end of the plates we would have some fringing happen, which means that the electric field lines can extend a little bit beyond the edge of the plates. And so we would always only look at like the middle section of the parallel plates so that we could avoid taking into account any fringing that might be happening. That's the same thing that we're talking about over here. We're going to say that we're looking at it's so long compared to the length between them that we won't have any of this fringing kind of effect to take into account. Okay, so the first thing that we want to answer is this one up here. What's the electric force between these two things? Well, since these wires are the same, they have the same number of protons and electrons in them, and since they have the same number of protons and electrons, they are electrically neutral. So there's no electric force in those wires. All right, now let's talk about the magnetic force F sub B acting on I2 because of I1. So obviously, I hope now you understand that the first step that we need to be taking is trying to figure out what the direction of the magnetic field would be in each of these scenarios. So since we're trying to figure out what the magnetic field direction is, we're going to use the curved finger right-hand rule. So I'm going to point my thumb in the direction of the current vector, okay? And so on this side of the current, the magnetic field lines would be pointing up, but over here where I2 is, because we're trying to figure out what the magnetic field is over here that's affecting I2. If I point up, my curved fingers are pointing down into the page. So that means that the magnetic field generated by I1, so we'll call it B1, is pointing into the page over here where I2 is. So that's what we're going to use here. We are going to say, okay, that goes into the page. Now we want to use our equation to calculate magnetic field strength because of a long straight wire that we learned about just a little bit ago. So here's our equation that we can use to find magnetic field strength. And this R1, the distance away from I1, is going to be the value D. So that's what we've substituted in here, okay? Now we're trying to find magnetic force, okay? So that's why we figured out what B is, so that we can plug it into our magnetic force equation. Remember, magnetic force is ILB sine theta. Okay, so we've got ILB sine theta. Now the I that we're going to talk about here is I2. Okay, the force that I2 is acting on I1 with. So if we look here, this B1, all right, we just figured out that that's this right here, okay? And so that's what we're going to plug in right here to the equation. And then you'll see that I'm saying that the force, the magnetic force of 2 acting on 1 is going to point to the left. The way that I know that is by using the straight finger right hand rule, because anytime we want to find the magnetic force, we'll use the straight finger right hand rule. Okay, so how do we do that? B1, we said that B1 is pointing into the page, so we take our right hand, we put the palm of our right hand so that it's pointing into the page. We use our straight fingers and point them in the direction of the current vector, right? So the length of current I2, that vector is pointing straight up as it's in the picture here. So we do that, and that means that our force, our magnetic force, is pointing to the left, okay? So we've got that our magnetic force is pointing to the left. Well, these are going to be equal and opposite to each other because they have exactly the same length as each other. This d variable is the constant, or is a constant. So everything about them is exactly the same, including the currents that flow through them. So because of that, they're going to be equal and opposite, which means that by finding out the force of 2 on 1, we've also found out the force of 1 on 2, except that that one, the force would be pointing to the right. And so how do I know that? Let's look at these two situations, okay? If we have both currents pointing in the same direction, then we can figure out what the magnetic field vector is going to be, what direction it's going to be in. So we already found out B1 is going to be pointing into the page because of the curved finger right hand rule. And now let's figure out here, if I point my thumb on my right hand in the direction of the I2 vector, then that means on this side of I2 over here, my field lines are going to be pointing out of the page. So B2 would be pointing out of the page. Now that I know that, I can figure out with the straight finger right hand rule what the force vector would be. So with my right hand, I'm going to point my palm out of the page, and then my straight fingers need to point in the direction of the current. I'm doing I2, so this vector right here. And then that means that my thumb over here is pointing to the right. So my forces here are going to be equal and opposite. They're attracting forces because they're pointing towards each other. If they don't point towards each other, okay? So for this one, let's see here. Since I1 is pointing up, all right, if I point my thumb up, then that means that my field lines are going to curve around like this. That means on this side over here, they're going to be pointing into the page, okay? Now let's do the same thing for this one. I point my thumb down, and that means that over here on this side of I2, the field lines are pointing into the page, okay? So now, if I want to find out what the magnetic force 1 is, the force because of this magnetic field, I'm going to point with my right hand, my palm down into the page. Then I need to point my straight fingers in the direction of the current vector, So I'm going to point it like this. That means that my thumb is pointing to the right. So the magnetic force is pointing to the right for that one. If I do the same thing here, point my palm down into the page for the magnetic field, point my straight fingers up in the direction of the current, then my magnetic force vector is going to be pointing to the left. That means that they repel each other. Okay, so we can kind of set up some relationships here, a proportion statement. If the current runs opposite to each other, as I'm showing right here, then we would get repulsive forces. If they're in the same direction, we would get an attractive force. Okay, so we can kind of plug back into this same equation that we have here, and we can see that, okay, L is the same, this permeability free space is the same, and 2 and pi are the same. Those are all constants, so we can ignore those. So the magnetic force is going to be proportional to I2 times I1 over d, the distance between the two wires. And we can just remember that opposite direction means repel, and same direction means attract. All right, hopefully you found that helpful. Thank you for learning with me today, and I will see you on the next one. Bye.